That works. Thank you very much. Thank you for your time listening to my presentation. As I mentioned, I am a state bridge design engineer for Washington State DOT, and my job is bridges. And my presentation also is focused on bridges. We are talking about some innovative material and seismic aspect of design for post-earthquake functionality, as well as the durability and so on. The topic for this presentation is intervention and rehabilitation, transportation infrastructure through advanced material, technologies, and construction methodologies. So the presentation includes the innovation in bridge design and construction. We are going to talk about the precast bridge system for accelerated bridge construction, ultra high performance concrete, post-earthquake functionality, and self-centering piers using precast bridge columns and concrete fill steel tube for seismic resiliency and for accelerated bridge construction. We did have some projects, and we go through some implementation that we had from accomplished research project. And also at the end, we are covering tunnel as we do some bridges and tunnels in our office. So we did some innovative work on tunnel. So moving on, the seismic in general has its own complexity, but especially when it comes to Pacific Northwest, it has some complexity related to the region. We are dealing with the Cascadia subduction zone, and that's just could create a massive earthquake as well as tsunamis, similar to what I've seen in 2011 in Japan. We do have some local faults as well as some liquefiable soil. So we are in Alaskan glacier basin and deposits, so the soil is not as good and as reliable, so that and also subjected to liquefaction. And recently the focus is the basin amplification that we have in most of the Northwest Pacific Northwest, and that one is the basin effect, and is being researched by University of Washington, and also is covered by the AASHTO guidance specification for performance-based seismic design that has been done. So with all this, seismic become more interesting and more challenging in our area. We are in a seismic zone C and D, and most result the seismic design category also C and D. That's challenging for us. The other issue that we have within the seismic design, we are looking for seismic resilient bridges. So that's ties to the concept of Lifeline. Lifeline are those roads and bridges and other structure within that area that allows post-earthquake functionality. So that could be either limited functionality for emergency vehicle, as well as for open to all traffic after subduction. So in order to achieve that, so we got to ramp up the design that we do in order to make sure this structure could go through the seismic demand design earthquake, but also to survive in order to get back to service. Along that, as I mentioned earlier, the geotechnical hazard that we have, that including liquefaction, lateral spread, and landslide due to the location of the Pacific Northwest, that area. And so the seismic design criteria for bridges are categorized as essential. So in this, it could be recovery bridges, critical bridges, and post-earthquake functionality requirement to immediate access for emergency vehicles. So starting with the ABC bridges, so accelerated bridge construction is also hot topics, and we had a project called Highways for Life, and that's in south of Olympia, and the idea was to make the entire bridge out of precast element. That was a few years back, and in our area that we do have seismic, and we do want to have an accelerated bridge construction. But also we are considering the long-term performance of the bridge, which is a focus of this conference. So we are shooting for 100-year service life design, the guidance spec that was adopted by AASHTO 2-3 years ago. So putting all this in mind, and there is a little room for innovation within that performance design that gets in a way that meeting the ABC and meeting the seismic and meeting the performance requirements. So if you look at the typical bridge pier that's shown on the left side from the Highways for Life project, you see the point of moment and shear are at the connection. And the connection are those when you bring these prefabricated elements and put it together, and where the highest demand is. So that's become a challenge to get these things right now. So that requires some testing that we do with the grouted duct connection to put the precast segment together. And that was done at the University of Washington, and was a successful project a few years back. It's a grouted duct, and what we found in that project that since this grouted duct provides some confinement, so pulling the bar, developing the bar, large size bar number 10, 11, 14, through this connection, it requires much longer development length than the conventional bar development, and that's because of the confinement and the strut action that's between the bar bonding and to the metal duct that we had over there. So that was a good project that was taken from here and used in some project, a grouted duct connection. Several projects that we have used this grouted duct connection in order to meet the accelerated bridge construction. As you can see, the pier that take time to probably weeks or so that to be formed and put the rebar and cast concrete and cure that could be done within a few hours assembled on the job site. One feature we did work with the pocket and socket connection, and the picture on the left, it shows the socket connection. That's the bottom of the footing. And then either a circular column or rectangular column at the bottom, we turn the octagonal shape and or hexagon shape. That's for more uniform behavior on any direction, and also sawtooth in order to get the bond between the concrete and the precast column, not crossing the bar through the system. So then as part of Highways for Life, we did also some testing. The Highways for Life project was on a spread footing, as you can see on the right side. So we had to do some testing of the column to footing connection to find out what is the optimum development length that we need with having the plastic hinging at top and bottom of the column, not into the adjacent member, the footing or the cap beam that are by AASHTO requirement are essential elastic and capacity protected members. So we did that one theoretically as well as experimentally testing, as well as building a strut and tie model to just investigate, if we need the actual bar in the footing or not, so to get to develop this bar in a shallower foundation and making the plastic hinging as expected by Ashton. So the other thing that we have here, most of the foundation in Washington are on shaft foundation. So we did a similar test for column to shaft connection, and we played actually with the amount of rebar into the upper portion of the shaft. And with that, we came out with the optimum confinement bar into the shaft in order to get the non-contact backwards splice between the column bar and shaft bar, and to develop the plastic hinging right on top of the shaft, as you can see on the left picture over there. So this is being commonly used in some projects for column to shaft connection. And this is the project that was used, bought a total of 96 grafted duct connection, the segmental column with the 2-segment bent cap that was pretension, and then the superstructure was also precast deck bolt T-gear there. So entire pier, entire bridge was precast concrete. And again, we turned the column at the bottom to octagon, from rectangular to octagon shape, in order to more uniformity in behavior of structure. This is the completed bridge. It's been in service now, and everything is precast. I'm not going to go through that one, but columns are precast, cap beams are precast, the beams are precast, diaphragms are precast, and everything. But also, you've got to meet the seismic demand, and developing plastic hinging. The grafted duct also was separately tested with another project. So we're putting together. The only concrete that put this one, this system together, is the concrete on top of the lower cap beam in order to provide the integral joint, moment resisting joint that allows to have the plastic hinging on top and bottom of the column. And the one on the right shows the completed bridge, and that's featured from the PCI journal we had. Moving from that concept to another concept, we had a bridge that was collapsed as a result of the truck collision into the bridge. That was a span of the truss bridge, 4-span truss bridge that failed due to the accident. So we had to replace this bridge in 2 phases. Phase 1, it was an I-5 traffic, north-south near the Canadian border. So we had to open it to traffic using the temporary bridge, as you can see here, within a couple of weeks. And then after that, we had 3 months to build the bridge, and then to move out the existing bridge and put the new bridge in. So that was also concrete bridges with the connection between the 2. And that project was also tested. That project also was a cast in place concrete. We moved from the traditional grafted duct connection to a cast in place connection between the 2 girders, and that was a pin connection with some durability issues, long-term durability. We had reflective cracking on this kind of structures, but it was our first bridge that we used the CIP connection, and that also provided moment continuity for us. And that particular job, since we're meeting the existing weight limit, so we could manage to save 1 line of the girder. That was very helpful. One of the features of this project was also now NAFA splice that we had, so make sure that we can develop the bar within that small zone. So that project initiated some research project for us, and then using ultra high performance concrete to connect the two girders together. And also that was tested at the University of Washington and Washington State University to develop the UHBC material using local material. And then we used that material for the structural testing at the University of Washington. And that was completed. And we had since then 2 bridges using the ultra high performance concrete connection for girders. So these are some of the testing requirements that was done. The one on the right side is Washington University, just a flow test and basically mixed performance test, including spread test and flowability test and basic structural test, direct tension test. That's very new for concrete. That's usually used for steel, but we use that for concrete. On the right side, as mentioned earlier, so the development length of the bar, what would be the optimized length that we need to develop the bar in a non-contact lap splice at the University of Washington. And that was, we found out that we can develop this bar within 6 inches, but since it's a non-contact lap splice, so probably 9 inches is a good number that we used in our project. So that's now our standard practice for deck wall T-girders. We had previously limitation for the deck wall girder because of the grafted duct and welded tie connection that give the reflective cracking at the joint. But by going to the UHBC and cast in place connection, so that allows us to use this type of connection for major bridges as well, and is being successfully used. At the same time, we submitted for a CHRP project, and a CHRP project also is getting wrapped up, and that one is using for a complete bridge system with the UHBC connection, not only longitudinal joint that we tested, but also for the transverse joint at piers, so everything is connected to each other with the UHBC connection. As a result, as a successful, so we phased out the old deck wall T-girder that we had in Washington, replaced with the new girders that are, you can see in the pictures here. Moving on, another innovative material that we are using, concrete filled steel tube. And this is just using the steel can instead of reinforcement, and then having a reinforcement connecting the lower, the upper portion to the adjacent footing. These are some of the pictures that we had from the US-Japan workshop that they use for the Kobe earthquake retrofit, this concept. And then we brought these things a few years back, and we did some testing at the University of Washington on 2 different phases. And this is beneficial for us, mainly for foundation, to completely eliminate the need for rebar and also optimize the size of the foundation, because with that one you get a lot of capacity from the steel casing that's required for placement of concrete, and that becomes a structural portion. And that's some testing that you see in order to ensure that we can provide ductility once it's used in column and top and bottom of the column. So that's so that meet the SSI, soil structure interaction, and PY curve used in lateral load and seismic. So it's a good thing, and it has been used in several bridges in Washington. And this project is not new, has been started with a couple other projects, Caltrans and the US Army, and then with Caltrans and WCT, and then the last 2 projects was in WashDOT that's using to get this connection work for seismic zone. And basically the methodology uses the plastic stress distribution, the equilibrium that we have, and that's now adopted by AASHTO in order to get this design. We did have also a CHRP project initiated by Washtad from the column to cap connection to come up with the length that we need with concrete field tube. So that's also is on the right side, and these are the equation from the research project that's adopted by our BDM, and we are using in our projects. These are a early list of projects that used this new concept, and this list is growing now, getting bigger as we are going to have more and more projects. So we don't keep track on that. That became is a standard practice for us right now. And we do also have for application for column. That's also the column application is ties also to accelerated bridge construction, so we don't need to do any forming or any rebar or anything. So this is just a pile column combination that ties to the rebar, ties to the cap beam. So we did have some not testing, analytical development. We are hoping to get some testing done as the pile to crossbeam connection, how to develop that one. So the practice is right now we have an angular ring on top of that, and to develop the steel casing into the bent cap or pier cap or foundation. So that's been used. So one of the benefits is done by this study at the University of Washington. There's a bridge that conventional bridge has a 72 inches diameter column with lots of rebar, 42 number 11 bar. So structurally, you can reduce that one to a 42 inches diameter column with no rebar. Just assume it's a 3/4 inch casing that we had for that one instead of rebar, and then get the same performance as needed. So that has been used in many projects as it's shown here. With this concept is economical, meeting the seismic performance, and also better durability. Moving on, we talked about earlier about the Lifeline bridges, and within that Lifeline bridges, so we set the criteria, the more restriction criteria in order to have bridges within that area that has the survivability of the earthquake. So one option with that one is for recovery and critical bridges having a different set of the ductility. As you can see here, we have ordinary or normal bridges with the higher ductility. As you can see in the curve, you can go up to a point that bridge is still safe because we are designing for life safety, but not collapse or not loss of capacity. But this bridge may not be usable because it's out of plumb, and also may require a lot of repair in order to bring it back to normal, if ever.
Bijan, so, I'm sorry, we have 5 minutes.
Okay, essential and critical bridges. I try to wrap it up. Like critical bridges are those bridges that we are some limited ductility that allows the limited post-earthquake functionality to emergency vehicle as well as the service. So in order to do that, one option besides ductility is using a isolation bearing. We have used in quite a few bridges, and this extended the period of the structure, so reduces forces approximately by 80% going to substructure. So that's some demand on the isolation bearing, but it's very beneficial for column and substructure in terms of design. Moving on, this concept is applicable to existing bridges, the seismic retrofit that we did for the long-lasting bridges, make sure the bridge will survive the seismic. Another concept to get to this post-earthquake functionality was the use of shape memory alloy. That's familiar to most people. It was the first bridge in the US and using the nickel titanium alloy that allows was tested at the University of Nevada, Reno, like to say ED, and then this has been used in quite few bridges that it is designed, but one bridge actually used this material, and this is the first bridge in the US and apparently everywhere else that using this bridge and this the shape memory alloy allows to go to some level of drift and ductility, but when we unload it, it's come back to the original position. Along that, we use a concrete that is a ECC, engineering cementitious composite, that accommodate that level of deformation without just spalling or crack. Moving on, this is the bridge under construction. As I mentioned, this bridge is in service since 2019, and this is the first bridge of this kind that using the IPI. We are having a full fund requests in progress that using different type of material, most cost effective, that give the same super elastic behavior and self-centering capability. Other self-centering, I go a little bit faster through that, is using a precast concrete, but with center post-tensioning is unbonded post-tensioning. So this column has, as you see in the right, on the left side compared to conventional concrete, so you don't deal with plastic hinging and damaging the concrete or yielding rebar, but we get some rocking effect, and the pre-stressing is capable to bring bridge back to normal after the event. So in order that to happen, we put a limit of 30 to 50% of pre-stressing into the tendon in order to make sure that this is remain safely in elastic phase and capable to bring back to system to normal. And as part, so we are using a steel can on top and bottom to ensure that the column, bottom of the column and footing are not damaged due to this action, along with this some debonding so that we don't get the sudden fracture, localized fracture of the rebar within that zone. So this is some of the pictures of this self-centering being tested, and also some installation in the picture that you see on the right side. We could do the same thing with the CFST. We have a project in progress, and that's double shell CFST, concrete filled steel tube, that give the same type of behavior as you can see here, and came back to the center after the earthquake. There's a double shell, and the center is filled with this unbonded tendon as needed to assure the self-centering after the event. And since it stands on a steel can, so this bottom and top and bottom column are protected for that reason. So there are a couple other tests that has been done at the University of FIU, Florida International University, and that one by Professor and using this UHBC at the plastic hinging connection, as you can see here in this picture, and successfully with different application of UHBC above and below the plastic hinging zone, and as well as just at the plastic hinging zone. Both application was done and meeting the seismic demand. The other application could be using the shape memory alloy within the plastic hinging zone, and then we have the same behavior that we previously tested with the regular with the shape memory alloy and ECC, but here it could be with UHBC and getting the same behavior. Moving on, a couple of slides from the tunnel, Alaskan Way Tunnel that we built. This is also a signature structure and does a replacement of the viaduct. That one also was the same project as the superastic material. So the tunnel was also replaced in 2019, open to traffic 2019, and the viaduct now is gone, so you won't see that anymore. So as part of this project, we did some, the tunnel was a single bore tunnel, largest single bore in the world at the time of construction. I think it still is 57.6 diameter. So the focus of this couple of slides is just inside building the bridge inside the tunnel and using the accelerated bridge technology in that one. And these are the range of the single bore tunnel using a TBM. And this is the feature of our tunnel in Seattle. That. Moving on, this tunnel was entirely precast lining into the tunnel from one end to other. It's about 14,000 segment that was used in this tunnel to put this together. And the segment circular, and each ring has about 10 segments. That was a vacuum erected curve, and then with the post stationing longitudinal direction for the support of the bridge, and as well as the precast concrete for the deck part of the bridge, as you can see in that picture. So this is showing the precast deck. There was a precast pre-stress, pretension transversely and post-tension longitudinally, as you can see here. That was done, and then this bridge was again, this tunnel and bridge, including, was open to traffic in 2019. So with that, my last slides, accelerated bridge construction could be achieved in seismic region using innovative design and construction material. Microstructure of UHBC allows a durable connection resistant to corrosion, chloride penetration, and freeze-thaw. This is what we are looking at. More use of UHBC, not only at the connection, but also bridge beams. Deck girder use UHBC connection, as I mentioned that, and also bridge pier with self-centering capability, either shape memory alloy or CAM, which is the new generation, more cost-effective that we are looking for. Hopefully allows to achieve this self-centering for seismic resiliency and post-earthquake functionality. CFST is something that we are looking for, and projects using that kind of self-centering technique and UHBC connection. But also I'd like to mention that there are a lot of tests has been done, a lot of successful testing has been done. The part that is really missing is the implementation by transportation agencies of this kind of connection is new, that more and more designer contractors, familiar and material become more available and become more cost effective. And thank you very much. I share this slides, this presentation, and there are some just linked to some of the research and implementation. I talk about that, and also I'm available if there is any question or anything.